Today's talk is by Professor Manuj Mukherjee, and he will be speaking on multiparty interactive coding over networks of intersecting broadcast stints. Professor Mukherjee is an assistant professor in the IIIT Department of IIIT Delhi. He completed his PhD from IIIT Bangalore in 2017, following which he served his stints as a postdoc at Telecom Paris, France, and at Bar Ilan University, Israel. His research interests includes information theory and theory in general, with specific focus on multiparty interactive communication. Before we move on to the talk, we would like to request our online audience to keep your microphones on silent, unless you have any questions, and for any questions you may raise.
So hi, thanks for this nice introduction, and it's great to be back here. So today we'll be talking about multi-party interactive coding over networks of intersecting broadcast links. So this is joint work with my ex-postdoc advisor, Bar Ilan University. So let's parse this first. What is interactive coding? So, when like one-way communication, you want to send a message and you want to protect it from noise, you do some coding. Similarly, if you have interactive communication, interactive coding is just the coding for interactive communication to protect interactive communication from noise. So the next question should be, what is interactive communication? So interactive communication is just like when multiple parties talk, as if they're interacting. That is, the messages they send depend not only on their inputs, but also on what they have heard so far, right? And this is something that arises naturally in any kind of a distributed computation, distributed communication setup like Internet of Things and all. But for those of us who are more into theory, interactive communication is also very interesting because for certain communication tasks, interactive communication actually reduces the amount of communication you perform to complete that task. And so let's begin with such a toy example. So here we have two parties, A and B. A happens to be a football fan, and so they know that the final was between Argentina and France. They just don't know who won. Somehow they missed that. He doesn't watch football. Somehow read from news that Argentina won. There's no clue who played the finals. And the task is as follows: B needs to communicate. But if interaction was allowed, we could do this in 4 bits of communication only. And let's see how we can do that. So A knows that it's either Argentina or France. It cannot be any other team because he knows the final. So what A does is the following. She looks at the 5-bit representations of Argentina and France. There must be at least one index at which they differ. So what A does is codes that index and sends it to B. So there are a total of 5 indices. So how many bits will need to code that index? Well, ceiling of log 5, that's 3 bits, right? And what B does is simply sends the bit corresponding to Argentina for that location. Okay? And from that, A immediately knows that okay, it has to be Argentina. So this took how many? 3 plus 1, 4 bits. And in general, so if you have n teams, so the non-interactive communication would mean you directly send the encoding of the team. That's log n bits. Whereas if interactive communication was allowed and you use this strategy, well, you will need first out of the log n locations, you can encode the log n location, that will take order log n bits plus 1 more bit. So in total, you will require order log n bits only. So you have an exponential drop in the amount of communication you require.
That's side definition. That's side definition.
What do you mean by like?
That means there is sufficient for you to just get that difference in the location.
Right.
If you did not
No,
know this,
we have the side information even in the non-interactive setup as well, right? We definitely
no, for
know
example,
that.
I do not know what we know. We do not know what I know.
Yes.
We don't know. Then it's-
Right. No, so we know that A knows the finalists, right?
That's the extent.
Right, right.
That's what I think.
No, but it's a very fixed task. And even for this task, even we know they know the finalists, we doesn't know who the other finalist
No,
was.
I get it, but I'm saying it's the extent. He knows that he knows.
Right. So in this setup, this is a toy task, but we see that non-interactive communication is strictly worse than interactive communication. And there are construct other examples. So this is why interactive communication is important for us theorists. And now the question is, so how do you protect such interactive communication from noise? So before we go to the multi-party setting, let me formally define an interactive communication first in a two-party setting. So in two parties, you have two parties, Alice and Bob, because people have never named the two parties anything other than Alice and Bob. And they have the respective inputs, X and XB. This could be from any set, I don't care. Okay. And they're running a two-party protocol pi. Okay. So what is the protocol? A two-party protocol is nothing but a bunch of rules that tells the parties what bit, who sends the next bit, and what bit to send based on their inputs and what they've heard so far. So let's say the protocol first tells Alice to send the first bit. And this depends only on the protocol sets what this bit is based only on its input. Let's say Bob sends the next bit, and now this depends, the protocol decides what this bit is depending on its input and what it has heard so far. Okay, the next one is sent by Alice again. Now this depends on Alice's input and what has been communicated so far. And it go on back and forth like this for, let's say, R rounds. Okay. So the output of the protocol is the set of messages that were exchanged. Okay, which we also refer to as the transcript of the protocol. Now all of this works out fine as long as there is no noise. Like whatever Alice is sending, Bob is receiving, whatever Bob is sending, Alice is receiving. And the question, the main goal for today's talk is what happens if there is noise? In other words, can we obtain some kind of a noise resilient coding scheme such that Alice and Bob can recover the transcripts with high probability? So let's formalize what I mean by a noise resilient coding scheme. Yeah,
So even without noise, it's an interesting question, right?
yes. So without noise, the seal prices study now there, you need to do something with the transcript. You probably use it to compute some function. And there the goal is like, okay, if I fix a function, what is the best protocol for computing that function? So the question of communication complexity.
Pi.
No.
Same function.
So this is just a bunch of messages exchange, right? Now what do you do with these messages? Like sometimes what would happen is Alice and Bob wants to compute a joint function of their input.
I see.
Right? So, and then the question is, you could do it many ways. Like you can simply, Alice can send XA to Bob, and Bob can compute the function and send it back to Alice. Right? That is still interactive communication, but this need not be the best thing.
The goals could be even simpler, right? Just I want to know, Bob wants to know XA and Alice wants to know XT.
Yeah, that's also fine. So in all of these cases, now then comes the goal of what is the minimum amount of, like what is the protocol with the smallest R. So in the noiseless setting, this is the question that is studied.
Well, I mean, what you're not telling me is the M1, but to me seems like the question would be to minimize the number of bits to represent M1 to MR, right? In total.
No. So M1, M2, M3, MR are bits. Right.
I know, but I'm saying that you can have a pi which gives more bits first time, but then you have less number of rounds. That is cheating, right? What you would want is, in general, the total number of bits exchange should be the minimum.
Yes. Exactly. So that's the goal. That line of work falls in communication complexity. So Dimanshi used to take a course on that when I was a student. So, but that's a very different kind of thought. Here we don't care about what is done with this transcript. Here our goal is like a coding series. I need to reproduce exactly this transcript with high probability, of course, in case these are affected by noise. Okay. That's my goal. So, what do I mean by a noise resilient coding scheme? So recall that in one-way communication, what does a coding scheme do? It takes as input a message and spits out a code word, right? So that if you transmit that code word, even if part of it gets corrupted by noise, with high probability you will still be able to recover the message from it, right? In interactive communication, the coding scheme is as follows. It takes as input any protocol file, so that any protocol meaning any bunch of rules to update what the next, to calculate what the next update would be of our transmission, and it outputs a new protocol pi dash of our dash transmission, such that when Alice and Bob run this new protocol pi dash over now a noisy channel, let's say they get transcript m dash a and m dash b, and these now can be different because the channel is noisy. So whatever Alice views as the message is sent over the channel need not be same as Bob, but based on whatever they receive from the channel, they should be able to obtain estimates of the transcript of the original protocol. And just as in the one-way communication, how do you evaluate a coding scheme? Well, you evaluate it using the probability of error, that is probability that either of the estimated transcripts does not equal the original transcript of the original protocol. Okay, and the goal is exactly the same as one-way coding scheme, is minimize the overhead of coding, in this case r dash by r. R dash recall is the number of transmissions of the coded protocol, subject to the condition that the probability of error vanishes as r becomes larger and larger. So is the problem clear? Okay. This is the two-party problem. Yeah.
So there were many transmissions. So that was in the end we have MR.
Yes.
So if any one of them get noisy, it will affect any one of its output.
Right. So this is a good point, and so that's why this is the point I'm going to come to the next slide immediately. So what you just pointed out is actually a very important thing. Is so why do we require something called interactive coding? We already have off-the-shelf like error correction codes, and the problem is they won't work because of exactly what you pointed out. So remember, even if R grows, like the message becomes, so first of all, error correcting codes work for large messages and large blocks, right? Now, even if R grows here, at any point of time, both the parties know only one bit, the next bit that they need to send, right? And therefore, at any point of time, you only know one bit. What's the best thing that you can do? Well, you can repeat it. Repeat it. That's the best thing that you can do.
Are you assuming that each m is just single bit?
Yes, or it could be a constant number of bits. By constant, I mean constant in terms of
Which is
not
necessarily just one.
not necessarily one bit. A constant number of bits is also fine, but it is constant. Like it is not
So
dependent.
one thing you understand that when you say m prime a of r prime, right?
Yes.
This is not just the encoded version, but what you're gonna see is not encoded version. I don't know what kind of noise it is. Then you're gonna get
So
that
now is
plus-
going to be we are going to assume binary symmetric channels.
So what you're gonna get is a distorted version of it, right? Not what you send, like pi,
Right.
that is not really.
Right, right. So this is why these two are not going to be the same. So let's say Alice sends M1, Bob will get M1 dash. So in MB, M dash B, Alice M dash A will have M1, but M dash B will have M1 dash, like this. And then Bob's next transmission will be based on it has this dash.
For that part. So if you did not have noise, you would have used protocol pi.
Right,
Now if you have noise, you are using protocol
Pi
pi
dash.
prime.
Pi prime. right.
Okay, and you were saying that after pi prime, this extra noise, and then would you see this m prime? Is that okay for me?
Right. So pi prime, like every communication gets affected by noise.
So before
So suppose
pi was m, so you're saying pi prime, and the noisy version of that is m.
exactly.
Got
Okay. So coming back to the point, so at best what you can do is repeat that bit, right? So now we write down all the possible strings Alice can send, all the possible strings of playing card that Alice can send over as a complete binary key. So each of the strings would be a different path down from the root to the leaf of a complete binary. Then you take the articles. You will see why this view is important. Interesting to us. And this is all the possible strings that Bob can decode based on what Alice said. Now, so Alice will be encoding this one by one if you are just going to repeat the bits. And so the other thing is, if you repeat a bit across a binary symmetric channel and you decode it by the majority rule, then you can show this I mean, you can try to work this out as an exercise, that the probability of error is 2 to the power minus theta of rho. So this theta hides the constant, which is like relative entropy between half and epsilon. I am not mistaken. So rho is the number of visitors. So suppose say Alice first sends 0, Bob equals 0, but then Alice sends 0, Bob equals 1, and immediately, as you pointed out, it goes in error, and there is no way to recover this product. So what's the probability of error? Well, roughly you have R transmissions, right? And in each transmission, probability of error, this is just on Alice's side, there's also going to be on Bob's side as well. So on each side, the probability of error per transmission is 2 to the power minus theta rho. So roughly it is R times 2 to the power minus theta rho. So forget vanishing, even to get a constant probability of error, okay, you would require your rho to be at least order of log R, right? That means you have to repeat each bit order of log R times. So what's the overhead then? R dash by R is order of log R. And this is highly inefficient because there are better schemes which achieve a constant overhead O of 1 here. And for that, you require a entirely different set of coding tools and techniques, which is what we call interactive coding. And that is why it's an interesting problem. You cannot just solve it using error correcting codes. Okay, so now let us actually go into the setting that we study, that is the multi-party setting. Okay. So when you go from two-party to multi-party, there are two things to talk about. Two things to take care of. The first one is in the two-party, Alice and Bob are hearing each other's transmission, right? In a multi-party comes the question of who hears whose transmission. Like, does everybody hear everybody's transmission or in yes? So in generally, you model this who hears whose transmission as a network. Now, this network will be a network of point-to-point links. That is, every pair of parties connected by a dedicated point-to-point link can hear each other's transmissions on that link. Or you could look at a network of broadcast links where there are sets of parties who can hear each other's transmissions. The second thing to look at is what is called order of speaking. Now, in the examples that I was showing you, there you were seeing Alice and Bob were talking in an alternating fashion, right? More generally speaking, this was what is called a non-adaptive order of speaking. That means the order of speaking was fixed beforehand. It was not depending on the messages that was received. Okay? So similarly, in a multi-party setting, you will have a non-adaptive arbitrary order of speaking. That's one possible thing that you fix beforehand that who speaks at what time. Okay? Then a very, very special case of this is called the fully utilized. So this is another non-adaptive order of speaking, or the special case of that. What does it mean? Here the protocol proceeds in rounds, and in each round, every party sends one and only one bit, okay, along each link it is connected to. This is the fully utilized order of speaking. And then there's a more general adaptive order of speaking, where nothing is fixed beforehand, and based on the messages that each party receives, it decides whether it should send a message in the next round or not. Okay. So in this talk, we're going to look at, as the title suggested, we're going to look at networks of broadcast links, and we're going to only consider the order of speaking being fully utilized. That is, per round, every party sends one and only one transmission along each link it is connected. So let us now look at the specific network topology that we are going to study. So it's called single point intersecting broadcast links. So the network topology is follows. You have N2 broadcast links, N2 equals to 4 in this picture here. So N2 broadcast links P1, P2, P3 all the way up to Pn2. Each broadcast link has N1 plus 1 parties. So in this case, N1 is equals to 3. So in total, each link has 4 parties, such that one party P0 is common to all the links, and all the other parties belong exclusively to only one link. Okay. So for example, we label the jth party of the ith link as Pij. So let's take the first link, the parties are P11, P12, P13, and so on. Okay. So what is the total number of parties? So we denote the total number of parties by n, and what is the total number of parties? So there are n2 links. Each of those n2 links have n1 parties exclusively belonging to it. So that contributes n1, n2, and there is one party common to all.
So just to understand this.
Yeah.
P11 sends, then everybody in the P1 link can hear, right?
Right.
P1 to P1.
Yes. Right. And it's a very good point to think about because that's exactly the next one I'm going to talk about. What happens when P0 sends?
P0 and everybody here, right?
Right. No. So this is the assumption. So P0 can broadcast along each of these links. So when P0 exactly. So when P0 broadcasts along P1, these three get to hear it, but these three don't get. None of these get to hear it. P0 broadcasts along P2, only these three get to hear, and none of the others get to hear.
Nice. I don't know the model, but I feel like this M2 is okay, but M1 could have been for each link separate with not changing.
No, it will change. So it will depend on, as we will see, it will depend on. You can change it, but its relationship with respect to N2, like whether it is polynomial in N2.
Because it seems like all the beams are some sort of independent. They don't depend on others except for P0, right? So
No, but the point is okay. So where this will matter is parties in this link will have to agree on a bit. Okay, what was being broadcast, right? If you increase the number of bits that has been number of parties, then one of them might go in error, right? So you need to ensure that the probability that all of them, gets all of them correctly decodes a broadcasted bit.
No, what I'm trying to why the symmetry number of parties in each link that I.
So even if it is not symmetric, but as I'm trying to say, if N1 and N2,
No, N2, I don't think, because this is just
right.
the number of links.
So let's say
it could be.
you have N11, N12,
correct,
N13, N14, right?
Yes.
As long as they have a certain order, like all of them are, let's say, polynomial in N2,
Which is fine.
or all of them, then our scheme will go through. But let's say if one is polynomial in N2, the other is an exponential in N2, then
these things are just for theory. In reality, what will you get numbers? Nobody creates a sequence of these things, right? What I'm saying is that you're gonna get different numbers and it's okay, right?
Right. So that in theory, what you do is like as the network grows, you
know what you're talking about. But in general, it just sees some number in each. Okay.
Yeah. Okay. So now let's define what we mean by protocol now. So protocol again is a bunch of update rules. Okay. So here the protocol proceeds in rounds. So R rounds and in fully utilized rounds. So what does it mean? So that means that suppose we are at round R, at the beginning of round R. So R minus 1 round has taken place. So let's consider a party Pij. How many bits it would have received so far? Well, if it's Pij, it belongs to one dedicated link, right? In each dedicated link, there are N1 other parties other than Pij, right? Okay. And in each round, because it's fully utilized, everybody sends one transmission. So in each round, Pij receives N1 bits. So in total, R minus 1 rounds, it would have received R minus 1 times N1 bits. Based on what these bits are, the protocol pi is going to tell Pij what bit to broadcast next to Pi, to the link Pi. Similarly, for P0, here it would receive per round N1 and N2 bits, right, from each of these parties. Okay. So in total, in R minus 1 round, it would have received R minus 1 times N1 and N2 bits in total.
This part is not clear. So we need mean round. So now there are multiple links as well, right? So,
right.
So when you means
one round
is P0 sends, P11 sends, P12 sends, or
so everybody sends one bit along each link it is connected to. That's the definition of fully utilized.
Okay.
So P11, P12, P13 will be sending one bit only because they have only one link connected to it.
But this is not end. Then P2, P2.
So all of them would be sending one bit along their links in one particular.
And all the links.
Yes, all the links. So P0 would be sending here actually N2, but in this case 4 in one round, but one along each link. So similarly, based on whatever,
so basically round includes all links.
Round includes all links. Right. So based on whatever P0 has heard so far, what these bits are, the protocol will tell what bit it should send broadcast to each of these different links, right? Because P0 needs to broadcast one along each. That's what's the definition of fully utilized. And this goes on for R rounds, and the output of the protocol is the transcript. That is, every party outputs whatever the bit it has heard so far. That's around.
So I'm still not getting the motivation for this graph because P0 can hear everyone, but anyway they transmit only along a beam, right? Or a link, whatever you say. So,
Right.
So why does it matter if I get from others? Because I'm not using the information to send anything.
No, I am using it.
But how would that help? Because P2 and P1 may have no message of interest to each other, right?
P2 and P1? No, but they may, right? So the point is like, for example, if you have these guys and they want to communicate with these guys, like run a protocol.
Are you considering that? They all want to.
Yes.
Fine.
So if you want to do that,
see like they're all sort of orthogonal things and this P0 there it can hear everyone, but doesn't matter.
No, it does matter because whatever see, it depends on the next broadcast. So each of these links depends on all the bits it has heard so far.
Right.
So whatever it sends to P1 depends
So
not only what it has heard so P1, but
all
also
want to communicate with each other, but the only one person can do this through P0 because
Right. The set of lines. So I mean, the theoretical motivation of studying this is so till now there were people had only considered one broadcast link. So we were the first people to actually try to look at networks, and you cannot. I mean, as you will see, this is itself very.
If everybody wants to talk.
Yeah. And the goal now is simple. So goal is like suppose these things are these communications get affected by noise. I'm going to define what noise model is. Goal is simple. Can we give a noise resilient coding scheme such that every party would be able to recover the transcript of the original protocol with high probability, and this scheme should have. I mean, the output protocol of this.
So how do you define noise resilient? Are you saying that as R tend to infinity, this is good, but then what do you mean by least number of rounds? So what is noise resilient?
Yeah, so noise resilient means that the probability of error. So recall the two-party definition. So here also everybody gets an estimate of the transcripts, right? And whether that estimate matches the transcript that you have gotten in the noiseless case.
No, the other case was very clear. You said that probability error should go to 0, and
Right.
you tell me the best way.
Right.
But
So here also R
is
is going to go to 0. R is going to go to infinity, number of rounds.
right.
And as R goes to infinity, probability of error should go down to 0.
Right. So what do you mean by least number of rounds? You're going to infinity.
Okay, so sorry. So I mean, this might be a misleading. So what I'm trying to say is the overhead.
Okay.
So R dash by R, like
Yeah, so you should.
yeah. Sorry. So this is a bit.
Yeah,
I agree. Right. Okay. So a bit on the noise model. So all transmissions are binary. So suppose somebody in some link is broadcasting the bit X, then each of the N1 remaining parties in that broadcast link, each of them hears an independent epsilon noisy copy of that bit. Epsilon noisy copy means you flip it with probability epsilon or you keep it as it is with probability 1 minus. And so this model is called a binary symmetric broadcast model. And the noise is independent not just across receivers, but it would be across senders, across rounds, across like for every transmission, all the noise would be independent. And here's our result. So we give a coding scheme such that which if it takes an R round noiseless protocol, phi, it gives a noise resilient protocol with an overhead of this number Hn1 and 2. And what is this number Hn1 and 2? So it depends on the relationship between N1 and N2. So for example, when N2 is at most polynomial in N1, the overhead is order log of N2. When it is between polynomial and exponential, it is order log of N2. Between exponential and something very high, 2 to the power of 2 to the power of small o N1 log N1 by log N1. It gives order of log N2 log of N1 by log N1, and if it is even higher than this, then this is the overhead. So this completes all possible relationships between N1 and N2. And now comes the first question. So when you see a result like this, one thing is of course how we prove it, but we'll come to that later. But first, how do you evaluate such a result? The first thing to ask for is optimality. What do I mean by optimality? That can there be another coding scheme, right? Which also gives a noise resilient protocol, but with a lower overhead, strictly lower overhead than HN1. And this is an extremely difficult problem. So this is of course not. Except in one very specific case, which I'm going to talk about in the next slide. And in that case, our scheme is actually optimal. So this is completely open if you want to try and figure out
I'm
what's
surprised that that is optimal. That means that log n1 is always there. I would have thought that in some weird world, this h of n1 and 2 is constant.
I mean, unless N1 and N2 are constants. Like,
No, n1 and I don't know. Like so, and otherwise you're saying that the overhead also increasing them very slowly, but still
very slowly, but yeah, it is increasing.
N1.
So that is the thing. Like, if you have a large number of parties and you want all of them to correctly, the probability of error means like any one of them decodes the wrong transcript, you are gone. So to ensure that everybody does it correctly, you require these huge overheads. Okay. And turns out that at least in one case this is true, and there is also some indication that this is also tight. And one sub case here is actually tight also. So it's not that you can do any better. But as a whole, we don't know whether it is optimal or not. So the next thing what you do is, if you don't know if it is optimal or not, then you check if there is some kind of a state of the art to which you can compare. Turns out that our result was as I mentioned, the first result which looked at interactive coding over networks of broadcast links. So there isn't really a state of the art, but let's try to manufacture some state of the art. Okay. But by manufacture, I mean that. So there is a very standard interactive coding scheme called Kuhlmann-Radhagopalan scheme, which is used for interactive coding over networks of not broadcast but point-to-point links. Now you can tweak that scheme a little bit and you will get a scheme for broadcast links. If you do that, you will get an overhead of order log n. And ours is a strict improvement. So let's just see one case. Suppose n2 is at most polynomial in n1. Now recall n was n1, n2 plus 1, right? So n and n1, the relationship is n is polynomial in n1, right? So what is log n1 and log n? They are exactly of the same order, right? So if it was order log n, then it's same as order log n1. Here we are getting order log n. It's an exponential drop. Then the basic scheme that you can think of, like you can if you lift Radhagopalan and Kuhlmann and make a scheme out of it, then our scheme is actually improving it exponentially, at least in this way. So similarly, in all regimes, you can see that it is actually improves. Okay, now two extreme cases of our setup has already been studied. And in fact, these two were our motivation sort of to study this. So the first extreme case is when n2 is 1, that is you're left with a single broadcast. So there's a very, very old result by Gallagher from 88, which looked at one round noiseless protocol. Okay, so what is a one round protocol? That means everybody has a bit and they just simply wish to escape. So everybody wants to know everybody else's bit, right? And Gallagher showed that in presence of noise, you can do this with high probability with an overhead of order log n1. And if you look at ours, this one falls into the first regime. Ours we give generalize this to general R round protocols with exactly the same method. It is known that this guy is tight to a result by Goel, Kinder, and stints. Of course, we don't know that whether this is tight. This type does not immediately imply that this is tight. So, but there's an indication that this might actually be tight. This is what I said. There's an indication in one place it might be tight. And here's the other case where it is actually known to be tight. So this is the other extreme when n1 equals to 1. So if n1 is 1, then every broadcast link has only two parties, P0 and the other party that belongs exclusively to that link. So it becomes what a star network. And for star network, there is a scheme by Braverman et al., which has an overhead of order log n2 by log n2, and this is exactly the overhead that our scheme obtains. Okay, and this overhead is actually not to be tight. So our scheme is actually optimal at this point. Okay, so this finishes the description of results. So now we're going to go into proof techniques.
So how different is your protocol from the Braverman?
Sorry.
Because this seems like in the same spirit, right? Yours
right. So the spirit, essentially, what we do is there is this Radhagopalan Kuhlmann scheme. We embed, like when it looks more like a broadcast link, we do modifications of Gallagher scheme and embed it sort of like an inner code within this Radhagopalan Kuhlmann scheme. And when it is on the more starry side, that is the last regime, there what we do is sort of embed the Braverman scheme within this Radhagopalan Kuhlmann scheme. And there we identify exactly at which regimes like what does better. So the entire set of proofs is quite involved. I will not be able to go through this in a 1 hour talk. What I will actually do is try to motivate, like not motivate, try to like give you like ideas as to how do you do interactive coding. This is a very different problem. It's not like one-way coding. So what are the tools and techniques that you do? So before I go there, any questions up to this point?
How does one get started in such an area? This is a good question. So if they're not asking us.
Right. So the best thing would be to quickly read up like a survey article or something. So my advisor has one, which is the only one. Ram Gares. Ex-postdoc advisor. They are not coming. So postdoc advisor. Okay. Rather ex-postdoc advisor. So you can read up Ram's notes. So that's a good introduction. There are some groups of like preliminary papers, like Schulman's paper, which we're going to discuss right now.
My problem with surveys are that they are sort of some very superficial and not
right.
So enough. So the field survey is good when you already know the basics.
I mean, so what I would say, surveys give you like what are the sort of the key problems in the area.
I agree, but that's not a good person to get started, right?
Right. So, but then you need to actually go deep and look at a few results.
So what is the first deep paper, which you can read and get something out of?
So Schulman's paper, I think, would be the first one, which is what I'm going to describe next. Schulman and Schulman Radhagopalan. Start with these two papers. If you like it, then I can like suggest more and more and more. So yeah, I mean,
I think it's always good to read the one paper which is the best in the area.
I think Schulman's recoding paper is the one we start with. That immediately gives you like what is going on in like what exactly do you need to do, and of course you can build your ideas after that. So some of the later papers do not use that idea at all. They go in other directions, which is fine, but you first get like grip of what exactly do you need to do. So that's how you start. And Gallagher's paper. These are the three I would suggest as the first paper. Then you can look at others. Okay. So let's proceed. So again, the tools that we will use for the multi-party case are similar to the tools for the two-party. I mean, one part of them is similar to the two-party case. The other part is different. So let us first begin with the two-party case. So a warm-up to the proof techniques. So these proof techniques are borrowed from Schulman and Schulman Radhagopalan, both. This. So again, I'm not going to give an exact proof here. I'm just going to look at the specific tools and techniques that we use. So to answer your question, that was actually a key question. If you make an error once, you're gone. And so you need to do something. Like even if you make an error, you should still be able to correct it. And that's the first thing that you will require. So again, like let's go back to the two-party case. Let's look at all possible strings that Alice could have transmitted and view it as paths down a complete binary tree. Okay, and this is what Bob decodes. So let's say the first one gets correctly decoded, the second one gets wrongly decoded. There's an error. Now you need to get back. The first key tool that you're going to require is a branch decoding code. What is a branch decoding code? So branch decoding code is an online code. In the sense, so online, it has to be online because Alice only sees one bit at a time. So it has to be encoded online. And per bit, it should be encoded. But using the decoding, you will be doing decoding on the entire string. Okay. So such branch decoding, so the kind of branch decoding code that we are going to use is called tree codes. And in the next slide, I'm going to talk about what they are. So using a branch decoding code, what happens is instead of decoding quite like the decoding is not online, the decoding is on the entire set of messages. And let's say Bob initially might have made an error here, but after seeing this transmission, I mean the code for 011, it would be able to get back 011 instead of 00 and then something here. Okay. So this is the first object that we require, which will be done through something called a tree code. We're going to come to what is tree code in the next. Now, question: does this only this enough? What do you think? Suppose we have something called a tree code. Is only this enough? So where could we go wrong even after doing a correct branch decoding? Oh, let me tell you. So at this point, Bob believed it has seen 0, 0, right? It only corrected it later, but at this point, it believed that it has seen 0, 0. So its transmission at this point would have been based on the fact that it received 0, 0, right? Right. So the protocol has already gone in there. So even if Alice had sent 1, whatever Alice sent here would be dependent on what Bob sent at this point, right? But that itself was the wrong message. So the protocol needs to be rewinded back to the source of the error and then restarted. So once you detect the fact that no, you have gone wrong, you need to tell the other party to go back. Okay? So this we will do through something called the parse operation. So these are the 2 key tools that are required for an interactive code. So let's look at these one by one. This is simple, this is the more involved. So tree codes. So what is tree code? So tree code is an online code parameterized by alpha. We'll see why this where this parameter comes into the picture. Okay. So it encodes strings from a DRE alphabet to strings from on some alphabet S of the same length. If it is an L length string from the DRE alphabet, we will encode it to an L length string on the S alphabet S. And it's an online code. So one way to visualize an online code is as follows: you draw the complete DRE tree, okay? And so each string will be represented as path on the root, path down the root. Okay? An online code basically is assigning to each of the edges, in this picture D is 2, assigning to each of these edges an element from this alphabet S, right? These may not necessarily be distinct, by the way. These are they're labeled differently, but they will not be distinct. Now, we cannot go for any online code. We need a very specialized online code which has the following property. This is where the alpha comes into being. So the property that is required out of tree codes is the following. Give me any length L, okay, and give me any 2 strings, DRE strings of length L. Okay. Then let us look at the encoding, tree code encoding of these 2 strings and obtain the Hamming distance. Then the Hamming distance must be equal to, must be greater than equal to alpha, which is the parameter here, times h, where h is the number of levels for which these 2 strings diverge. So what I mean is, let's say you take the red line and the blue. So these are 2 DRE paths, right? Okay, so their codes are S1, S4, S9 and S1, S3, S7, right? And they diverge for 2 levels here, right? So therefore, the Hamming distance between S1, S4, S9 and S1, S3, S7 must be at least 2 times alpha. Similarly, if you take the red and the blue, then the Hamming distance between S1, S4, S9 and S1, S4, S7 should be at least alpha. Similarly, between the red and the green, it should be at least 3 alpha. So this has to be satisfied for any pair of strings of the same length. There's a huge amount, there's a lot of, so you're demanding a lot out of this. Okay, and the point so the point here now is this. So how does this help? So why did we require this property? So this is what actually gives us the branch decoding capability. So what would happen is generally Alice would be sending its strings encoded into strings by through a tree code, and then Bob will be decoding it. Okay. So what would happen is we'll obtain a decoded alphabet with string. Since the encoding is online, you only need to send the final S signal. And it's a binary channel, so what would happen is if you encode it into, let's say, log of size of S bits, right? And then channel might introduce some errors. Bob will decode it to a symbol from S, right? So Bob will now have a string of symbols from S. So how do you decode? So decoding rule that we use is minimum distance decoding. So something you should be quite familiar with. But in the context of tree code, what it means is the following. So if I receive an L length string from the tree code output alphabet S, what I do is I look at all possible DRE strings of length L, take a look at their tree code encodings and find the distance between these and the received one. Whichever has the least distance, you output that string, and if there's a time you break it, you decide on an arbitrarily that some arbitrary rules of calculating. And I tell you that this actually gives us the branch decoding capability of tree. So how? So let's say you decoded this red line, and this was your correct. So they were the same up to this point, and then they divert for the last each level, right? So what does it mean? It means by the property of the tree code encodings, the encodings of this must have a distance of at least alpha h, and the distance would be, so the difference, and the difference in encoding can only happen in these h levels, by the way, because since the online encoding is online, at these points it should be exactly the same. All of them have the same symbol, right? And now, since you're using minimal distance decoding, y should be closer to the decoded branch, right? So if these two have a distance of alpha of h, then these two for the last h levels should have a distance at least alpha h by 2. What does it mean? It means that if you decode a string which diverges for a large number of levels, then it must be that in the last h level, because it is diverging for h levels, in the last h level, there was a lot of errors, and the probability of these events would be low. So this is how you get the branch decoding capability by this particular property of tree codes. Okay.
How do you construct this codes?
Yeah. So I was going to ask the next question here. So I was going to ask the students the next question here is, okay, are we missing something? So far I have been talking about like there is an online code which if it satisfies so and so and so properties, we get all of these nice properties out of it. Question is that does such an online encoding at all exist? Forget about like how we construct it. Okay. And by exist means okay, you can always put different symbols here, but that will lead to an alphabet of exponential size, exponential in the depth of the tree. So that is the bad thing to do. You cannot do that. Why? Because you're ultimately going to need to send these symbols across over a binary channel. If it's an exponential alphabet, think about it. So you encode it to be linear in the thing. So the overhead will be worse than the repetition code. So you cannot do that. You need something smarter. So Schulman, it's a great result from Schulman in this paper, who proved that given any alpha and any d, which is constant means constant in the depth of the tree, okay, there exists a tree code whose output alphabet s has size constant. Again, by constant I mean constant in the depth of the tree. It is, of course, it depends on d and alpha, but it is constant in the depth of the tree. So this is an impeccable result. So this alphabet is actually constant in the depth of the tree. Now to answer Paul's question, so till date it's an open problem construction for a tree code. An existence has been shown. There have been other things have been shown in the sense of like special varieties of tree code for palette alternating tree codes and all. An explicit construction till date is not known. What are known is if some hard problem can be solved, then you will have a construction for tree code. Results like this are known. Then there are relaxations of tree code which work for example, the two-party case. There are relaxations of tree code which will also be sufficient to do interactive coding. For example, potent tree codes. For those potent tree codes, yes, constructions are known. I mean, efficient constructions are known. Efficient meaning the encoding and decoding complexity is polynomial in the depth of the tree. So,
DM gonna solve it.
Okay, so I don't have too much belief in. Let's just put it this way. Since we're on the record, I will be off the record. I can say much more. But on the record, let's just say I don't really trust them. Yeah, so this is an open problem. So once you guys have a few numbers, so basically sufficient number of papers, you can try solving it right now.
People say that. So when people say decode, they're just saying that they exist. They don't know.
Yeah, just like initially we had for like there exists codes with this, achieve capacity. It was like long time before Runderberg gave the first explicit construct and fairly scored modulation. So similarly here, tree codes Schulman showed existence through a probabilistic argument, just like Shannon, there's a probabilistic argument. But they do exist, we don't know how to construct them.
You're gonna solve it, right? And get a China award.
If I solve it, this is going to be like big, but I don't think I'm nowhere close to solving. There has been a lot of research from some groups, but they end up at like if a hard problem can be solved, then there is a three-code construction. This is what then, or they like suppose I allow some amount of dependence of the alphabet on the depth, then we can get an explicit construction. Exactly this thing, still get nothing. And this comes about. So this is an IIIT transaction of information theory paper. It's women, I think, originally published in Conference or something in 92 or 93. So since then it's something. It's a long-standing, deep open problem. So and I don't know when there will be a solution to this. Okay. So the parse operation is actually simple. So we'll actually run the protocol that the coding scheme is going to out. It is not going to run on the binary alphabet, but on the ternary alphabet. So 0, 1 are the two information symbols which says we broadcast the next bit. But suppose the party wants to rewind the protocol by one step, it uses this symbol back. Okay. So, and parse is basically you remove an operation is if you get a string like this. What you do? How do you rewind a string? So the rule is you take out a back symbol, start from the right hand side, take out a back symbol, and take out the bit, the information bit immediately preceding. So what will happen here? This guy will take out this guy will take out this guy will take out this guy.
Sorry, so you mentioned on that right or right to left?
Right to left. I mean, it would be actually that it will not matter. And
No, because I'm not following which one they're removing.
So red with red.
No, I still don't get it. So you got 1 0 back, 1 back, 1, right? In that order.
Right. So what I'm going to do is we'll start from the rightmost back.
So this back is going to remove the second.
The first. Okay.
This back, right? This back is going to remove
this one. The information bit that immediately precedes it. So this is not an information. Right?
But I got two back. That means the previous back was wrong, right?
No. It could mean that there are two things to be like the strings. Suppose you decode a recoded branch, right? It turns out that you made a mistake for 2 levels or 3 levels. So you will have back.
Okay,
because each one is only used to rewind once. The reason, of course, is because you don't know whether the back that you're sending also gets translated, or whether you are yourself, like whatever you're decoding in that case, in that stage, is actually the correct decoding.
What should back get decoded? Because you say binary symmetric channel, right?
Right. That's the thing. So basically, what would happen is this will be our DRE tree. We're first going to pre-code that, and then pre-coded symbols we're going to represent it in log s bits and then. So I was going to answer that question next slide, but yeah, no problem. Yeah, that's good. I mean, that's good.
So I still didn't get it. So when I get this 1 0 back, 1 back, what is mine? So you remove everything before. So you have 3 backs, right?
So 3 backs. So I'm basically removing back, takes out this takes out this,
and this
takes out this. So only this one is
the last one.
And of course, protocol and the way we do the protocol intake. So what happens if there are more backs? Like any prefix of the string has more backs than information symbol. Of course, you get an error, but the protocol ensures that you never encounter a such string. So that's just a detail which leaving out. Now, so how do you combine these two things? So this is the protocol. I'm not going to give the proof of why this protocol works, but let me tell you how these two tools are used. So the protocol proceeds in rounds, okay. And I'm going to describe Alice's view. Bob's view is going to be exactly similar to Alice. Okay. So let's say R- transmission have occurred from both ends. So Alice keeps the following record. So far it would have sent R-1 symbols from 0, 1 decay, right? So Alice keeps records with string of all the symbols that is transmitted. Alice keeps a belief of all the R-1 0, 1 decay string symbols that Bob might have sent. Okay. And now, so as I mentioned, so it's a binary channel. So how does communication actually take place? You basically encode these strings to a precode and send a precoded symbol using bits, right? So every round, Bob is sending one precoded symbol encoded as bits. So you decode that to an S-valued string of R-. So you keep the record of what exactly S-value, that's r-1 length string of s value symbols, okay, that you have received from Bob. Now here's what you do. You first decode this string using the three-code decoding procedure, minimal distance decoding, right? So now you have three strings. The fresh belief, your already existing belief of box string, a fresh belief of what is box string, and a record of your transmission in 0-1 decay. All strings are now in 0-1 decay. You parse all three strings, right? Perform all the rewind that has been asked out. And then what you do is you check whether these strings are consistent with pi, in the sense that whether your freshest belief agrees with your already existing belief, and whether your transmissions based on the what you believe is box strings agree according to pi, right? Because depending on what box string, you would have transmitted something based on what is box string, right? And check whether that agrees. If yes, then you update the records and you're supposed to send the next information bit. Okay? If no, then you need to add back to your record, you need to rewind your records by one step, and you would also want to send the other party a vaccine. Now, how do you send this? So you add this 0, 1 or decay, whatever you're sending, to your already existing r-1 length transmitted string, right? So it gives an r length string 0, 1 decay. Now what you do is you recode this string. Since it's an online code, you only need to send the latest symbol. So you need to, every round, both parties need to send a symbol from S, right? And how do you do that? You basically encode this using log s bits and send it over the channel. Depending on the channel transition provided, the epsilon the binary symmetric channel, you might need to repeat it a few number of times, but the number of repetitions is going to be constant. Constant meaning it will not depend on the depth of the tree. It will depend, of course, on epsilon. Okay. And now you repeat these steps for O of r times. If you do this, then Schulman showed, we are not going to show this, but Schulman showed that this indeed is a noise-resilient scheme. Okay? Meaning that using this scheme, both parties will be able to, with vanishingly small probability of error, reconstruct these transcripts of the original product. Now, how many transmissions does this need? In every round, you need to send, both parties send log size of S bits, but size of S is constant. In every round, you send constant number of bits. And in total, there are O of R rounds. Therefore, the total number of bits you send is O of R, right? So, what is the overhead? O of R by R, so it's O of 1. Okay. So, this is what gives you the O of 1 scheme. So, how much time do I have? -5. Okay. So, let me just go over the next slide and then stop maybe. So, this tells us how to do in the two-party. Now, multi-party is a slightly different ballgame. So, let me just give like the basic outline of the multi-party group. So in multi-party, recall there were 4 regimes, right? So the first 3 regimes, that is when n2 is at most 2 to the power small o of n1 log n1 by log n1. This encapsulated 3 different regimes. Here, the coding scheme that you do, I mentioned this slightly before, is a layered coding scheme. So basically, what you do is you run a version of the Rajagopalan scheme, which is a scheme for the point-to-point network of point-to-point links. But you have to adapt it to the case of broadcasting. And in each scheme, what would happen is, again, so this is like a multi-party variant of Schulman scheme. So at every party you run the 2-party scheme. That is what the Rajagopalan scheme is like. So at every round, just like in Schulman scheme, you need to send a constant number of bits, log times size of S bits, right? And depending on how you send now, instead of just sending out these bits or just repeating these bits across the broadcasting, you can apply, like judiciously apply a broadcasting scheme, which we are calling a rate independent event code, a specific broadcast scheme, and that is actually what reduces the overhead. You simply repeat, you are going to get that order log n overhead, which we discussed earlier. And if you introduce something a bit more sophisticated, you are going to reduce the overhead a bit. In fact, in certain cases, we saw it was an exponential reduction. I won't be able to go down. So the remaining slides were about this, but I won't be able to go through the details of this. Then what remains is the last regime where n2 is really, really large. This is the study regime. Here we have to apply, basically you have to adapt the scheme for the star network by Brotherman. And this I was anyway not planning to talk about because this is a completely different ballgame compared to this. It's a very, very different scheme. So that's it, I guess. So the remaining slides were about how do you do these broadcasts, the broadcast protocol. So, thank you. If there are any questions.
I asked many questions.
So in the broadcast thing, can you just quickly go over it? How do you?
Oh, so okay, so this one. Okay, so the problem that it reduces to is now every party has the following thing. So every party has log s bits. In one broadcast link, every party has log s bits, and they wish to exchange all of those bits, right? So we reduce the problem to exchanging every party has one bit, and we are going to exchange those bits. Okay. Okay, so parties are going to exchange those bits, and they are going to run this log s time for each of the log s different log sizes. So the key problem is as follows: you have a broadcast link of size n+1, that is 10+1 parties, each of them holding a bit, and the goal is each party should recover another party's bit, except with probability n to the power of minus c, where c is some constant greater than 8. This comes from here, which we didn't go into. But if this happens, then we can show that the Rajagopalan and Kuhlman scheme has vanishing probability of error. Now, how do you do this? I'm just going to give you the basic equation. So the nice scheme, as I mentioned, is repeating it O of log n times. Okay. If you fix a constant here according to the channel transition probability and this constant c, you're going to get an error probability of this. So every party repeatedly sends its bits O of log n times, and you decode every other party decodes it using the majority rule. Now, instead of repeating in time, since you have a lot of other parties, you can repeat in space. What I mean is, for every pair of parties, you assign dedicated order log n parties. Then this constant will depend on c and epsilon, which would be act as relays, right? So now what happens is you you broadcast it bits once. Okay. Now these relays hear this bit. The relays are parties in that link only, and then whatever they hear, they forward it, right? So this is like a cascade of two binary symmetric channels. So which is also still constant in epsilon, like crossover probability. But now you have order log n. So you actually get an order log n repetition of the bit, right? And so by choosing the constant here carefully, this decoder would be able to get it with high probability. Now, of course, this is the key idea, but now you have to assign like which party for every pair of parties. How do you assign order log n? So this is the key part, but this I cannot go into anymore because this will not take time. So this you need to do something a little more than simply relaying as well. But this is the key idea. Instead of relaying in time, you relay in space. The key idea, but yeah, some more details are there, which I cannot go into. I can go it offline, of course. So, if you're interested.
So if you don't have any questions, you can close the session. Thank you.